This is lecture 2. So in lecture 1, I have a briefly talk about some introductory explanation about the game theory. And then we're gonna start the very basic form of the game, which is often called normal form game or strategic form game, especially with a focus on something called the pure strategy. You will see what it means. So the sort of the keywords that you will see throughout a couple of lectures, like lecture 2 and lecture 3, is a normal form game, strategic form game, and also the matrix game, because the payoff relationships are represented by a matrix, mainly because we're gonna first focus on the case where the strategy spaces are discrete. So since the strategy space is discrete, we can represent the relationship of the sort of the interest strategic situations within with a matrix. Okay, and then after that, we're gonna briefly talk about continuous game, where strategy space are continuous, which actually often occur a lot in practice. And also, we're going to see the word like structurally dominated strategy, pure strategy, mixed strategy, saddle point, and Nash equilibrium, and so on. Right? All right. Normal form game or strategic form game or matrix game, and then we're going to see the case where the pure strategy. Here, just a brief brief explanation about what the pure strategy is. Well, we're gonna learn something called the mixed strategy later, but the pure strategy is a purely deterministic strategy, whereas in the mixed strategy we can apply the probabilistic distribution of the strategy. For example, in a prisoner's dilemma case, I have a confess or silent, right? In a pure strategy, I can choose either of one, confess or the strategy, as you obviously expect. But we can have a strategy something like, I'm going to choose confess with probability 60%, and then I'm going to choose the silent with probability 40%. That's also a strategy. It's a random strategy. It's a probabilistic strategy. That is called the mixed strategy in the game theoretic terms. But that will be discussed in the later, but we're going to focus on the pure strategy case. Okay. Now, matrix game or a normal form game with the discrete strategy space, we can see this kind of thing. Okay, so if you see that, this is a matrix, right? In each term, we have two numbers there. So these are the players. Player 1 and player 2. Obviously, we can have 3 players, 4 players, whatever. But here, in this case, for simplicity, we consider the 2 players. And then these are the strategy set for player 1. Right? Player 1 can choose A or strategy B, and player 2 can also choose player A, B, and C, and B and C. Here, in this case, we look at the example where each player can have a different set of the strategy set. Like 2 by 3, right? And now this numbers represents the payoff to the player 1. But if you look at the payoff, player 1's payoff is the function of the strategy that is chosen by player 2. For example, even if player 1 chooses A, even if player 1 chooses A, then its payoff can be 2 if the player 2 chooses A. Or it can be 0 if the player 2 chooses B, and so on, right? And without this coupling, obviously game theory does not mean anything, right? I mean, player 1, player 2 should be independent. Now, players should be coupled together by defining this payoff function in this way. Like, my payoff is the function of the strategy that is chosen by player 2. Okay, right? And this is the payoff to the player 2. Again, player 2's payoff is the function of the strategy that is chosen by player 1. Okay? So this is a kind of a representation of a game, especially for the matrix game, where the strategy spaces are discrete, and so on. And we are assuming something called the simultaneous play. Well, the simultaneous play means that well, player A can choose A and B. Player one choose A and B. Player two can choose A and B and C. And then we tell each player to choose out of the candidate strategy choices, to choose simultaneous and then give me your strategy. That's the rule. This is a game rule. Right? It is similar to the situation where I give a sheet of paper to the player 1, I give another sheet of paper to the player 2, and please write down your strategy. And then obviously player 1 cannot see player 2's strategy, and the other way around also. And then I collect these two sheets of papers and then look at the choices. That's exactly the same as the simultaneous play. Okay, that's the game rule. Okay. Later we're gonna see the case where player 1 first choose the strategy, and then player 2 can read the strategy, can see the strategy by player 1, and then he can choose. That's a sequential. Okay, so we're gonna look at the later the sequential case, but here the basic form is the simultaneous play. All right, everybody clear? All right. Now, obviously, the combination of the strategy determines the payoff, right? It's like combination, like outcome, for example. Like here in this case, like A gives this payoff, but B gives that payoff, and so on, as we saw in the prisoner's dilemma. Yeah, I think everything is clear. It's pretty easy. So we can formally define the game with some little bit of mathematical notation. Which that is the representation of the normal form game or the matrix game. And we have a in a more general term, general situation. We have a finite set of n players, okay, like 2 players in the earlier example. And then also each player I has its own set of strategy AI, which can be different across each player. Like for example, player 1 has 2 strategy choices, but player 2 has 3 strategies choices. Okay. Now the payoff function UI, and it's actually different across the user, right? Because payoff are different for each player. And the S is a strategy vector. It is a strategy vector. And then S is obviously a member of A, where the A is a kind of Cartesian product of all strategy sets across the users, right? Right? Because it's a strategy vector. Okay? Like in earlier case, A comma B or A comma A. These are the one strategy vector in earlier example. So the payoff function is the function from a strategy vector to a real number, where that real number is given to each player I, and each player has a different payoff function. Okay, so A is a set of all possible outcomes. The strategy vector is outcome, and the S is a set of strategies chosen by players. It's actually a not set; it's a vector, right? Vector should be the right term. Yeah, a vector of. Ooh. Vector of strategies chosen by players, and then it defines the outcome, right? Oops. And then UI is the function where the domain is the set of all is a set of or collection of all strategy vectors or all outcomes, if you like. And it has a real number, and that's the range, right? And each payoff function is defined for each person. All right. Now we're gonna look at one of the most simple cases. one of the most simple cases where we're gonna consider only the two players, and then we're gonna some case where the zero sum games. Zero sum means that it's a summation of my payoff and the other guy's payoff are all equal to zero. Like for example, let's say let's say player A and player B. We have a strategy A, B, like C, D, where the payoff is 1, minus 1, 2, minus 2. Let's say here the 3, minus 3, and 1, minus 1. Let's say payoff function is like this. Then if you look at this case, the summation of the payoff in each case is 0, which means that it models the case where players' interests are strictly opposed, right? Okay. So what one player gains is equal to what other players loses. So in two-person zero-sum games, we don't actually need these two numbers. Okay, if you know that this is a zero-sum games, it's enough to represent the game with a one number, right? Like this. Then it means that other guy's payoff is minus 2 and minus 3 and minus 1. We know that. We implicitly know that. So game matrix has a single entry because it's a zero-sum game. So when the game is a zero-sum game, we can sort of simply represent the matrix, with one matrix, because the minus that matrix is the payoff to the other players. Okay. This is one of the most simplest case, and then as done in many analysis, we need to start from a simplest case, and then we need to generalize more and more and more and more and so on. Got it? All right. So we're gonna look at the two-player game and the zero-sum game. All right. Now, suppose that we have a game like this. These are the game formulation of the zero-sum game. Right? Now, suppose that you are given this this payoff matrix. You are given this payoff matrix. Then what are you going to do? We need to analyze the game. But by analyzing, what do we mean by that? How to analyze the game? What are you going to do if you are given this game matrix? What are you going to do? Okay, what are you going to do? Think about that. All right, one answer is that, okay, I'm going to look at this matrix for a long time, just looking at. But that's not the analysis, right? We need to analyze. So what do I mean by analyzing the game? Well, we need to predict. Well, at least we need to solve the game. What do I mean by solve? Well, we need to, out of many strategies, we need to figure out what will be the most likely the strategy vector that should be played by the each player. That is what we mean by the analyzing the game. So in order to do that, we need to conceptualize something called the solution concept. Oh, I believe that with this game, each player will choose this strategy. And that should have some clue about why is that. So the solution concept, essentially we need to choose the solution concept. So the solution concept is nothing but a formal rule for predicting how a game will be played. It describes which strategies will be adopted by players, and that's the result of the game. Oh, these are the game. I believe that the player A will choose this and player B will choose that, and that is the strategy vector that players will play. So if I have the question from other people that why do you think that this will be the strategy vector that each player will play? Because I have this reason, and I should be able to provide the good reason, right? So that's why the solution concept, there are many kinds of the solution concept because each person can have a different perspective, right? So it does not talk about how players will reach a solution concept, meaning that I believe that this will be played ultimately because this is a simultaneous game. But I'm not talking that probably, all right, each player will start from this strategy and then change their strategy in this way and this way and this way and this way and this way, and then it will converge this strategy. That's why I believe that this strategy will be a good strategy. No, that's a different story. So the solution concept is nothing but, okay, I don't know how each guys will reach this strategy vector, but I believe ultimately I believe that they will choose this strategy. I don't know the people's mind. People's probably inside the people's mind, they run some algorithm, but I'm not interested in the algorithm. I want to find the good strategy vector in some sense. So not naturally the solution concept is an equilibrium concept, meaning that's, well, if both of guys are choosing this guy, then probably after that both these guys will be staying at that strategy vector. All right? Okay? Now what is the next question? Next question is, what are the natural solution concept? Probably that's the first question. Okay, now I know the notion of the solution concept. Then what are the possible candidate solution concepts? Is there any solution concepts that everybody agrees with? Yes. We'll look at that. Okay. All right. So remember, still we are analyzing the player 2 game and zero-sum game. Okay. Since this is a zero-sum game, then you will see that there's one number. And this number means that the payoff to the player 1. So the player's 2 payoff is just a minus of this number. Okay, this is hidden. All right, this is hidden. This is hidden. All right. Okay. So since this is a zero-sum game, and then we will see that the player 1 tries to get a higher payoff, which means that the player 1 maximizes. Player 1 tries to maximize the number, meaning that the matrix entry. But here with these numbers, player 2 will minimize it. Why? Because if by minimizing this number, they will get a higher payoff. If they try, right? That's pretty natural. Because it's a zero-sum game. Does that make sense? All right. So let's develop the solution concept. There could be many solution concepts, but let's develop ourselves, right? What should be the thing? So we're gonna use the solution concept, which is motivated by something called the domination. All right. So what is domination? Okay. Yeah, that's what I explained before. So let's look at these two strategies. Now I'm looking at this choice. I'm looking at these two choices, and then try to compare this strategy. Okay, I'm looking at this strategy from the perspective of the player 1. So if you look at the player 1's payoff, this is 3, this is 1, this is 3, and this is minus 18. If you look at compare these two strategies element-wise, compare these two guys, compare these two guys, compare these two guys, compare these two guys. Then obviously for each element means that for each strategy vector that is chosen by player 2, irrespective of the strategy choice by player 2, player C will be better, right? Because the 5 is larger than 3, 2 is larger than 1, and 4 is larger than 3, and 3 is larger than minus 18. So why should I choose B instead of C, right? So in player 1's perspective, okay, obviously this is not a good choice. This is not a good choice. Player C is overly better than B. So we say that the player B is strictly dominated by C, because choosing C is better in all cases. So let's remove that. Now let's look at players 2's perspective. Let's compare these two strategies. And then players 2 tries to minimize that. So in order to, since it has to minimize, if we compare the element wise and irrespective of the choice of the player 1, this is better, right? Because it wants to minimize. And so in this case, the strategy C is dominated by B. So there's no reason to choose C. So I'm going to remove that. All right. Then we have just what? Here the B is removed and the C is removed. So players 2 only have like A, B, D choice. And the player A had only like A, C, D choice. Okay? And using this way, we can probably iteratively remove the strictly dominated strategy. Is there anything like that strategy? Let's say, let's compare. Oh yeah. So here in the players 2, this was removed, right? Let me see. This was removed. Okay, and this was removed. And then let's compare A and B. So it has to minimize that. 12 and minus 1. 5 and 2. Oh, minus 16 and 1. Oh, this is not the element-wise less. Okay, we cannot compare that. B and D. Minus 1 and 0. 2 and 3. And 1 and minus 1. Oh, I cannot remove that. What about player 1? Player 1, let's compare A and C. I want to maximize that. 12 and 5, and C is removed. Minus 1 and 2. Okay, it's not working. A and like C and D, for example. Oh, C and D is working. Okay, C and D here. 5 and minus 16, and 2 and 1, and this is removed, so we don't need to think about that. 3 and minus 1. So overall, C is better than D, right? So D is also removed. So using this way, probably by eliminating, iteratively removing the strictly dominant strategy, we can have a small set of the strategy vector, or in a lucky case, we can have just one strategy vector. And that is one solution concept. And that makes sense, actually. So strategy S is strategy S strictly dominates a strategy T if every possible outcome when S is chosen is better than the corresponding outcome when T is chosen. That's just strictly dominate. Dominance principle is that the rational players never choose strictly dominated strategies. That matches our common sense, right? I mean, that's why we call it principle. So idea is that let's solve the game. How can we solve the game? By eliminating the strictly dominant strategy, by iterated removal. Let's look at the example, right? So let's solve this game. So player 1 cannot remove any strategy, because if you compare these two guys, player 1 tries to maximize that, right? In order to maximize, okay, this is larger, but this is not larger, so we cannot remove that. So let's look at the players 2. In the players 2, if you see that, minimize that. So 4, 3. 4, 3 is obviously strictly larger than this guy if we compare it with M and R. So we can remove this guy. Now the player 1 can remove this guy, because player 1, this is strictly larger than this. Now since this is removed, we don't need to care about that. And this is larger than this is larger than this. Now I can remove this guy. I can remove this guy. Now 3 and 2, obviously I can remove this guy. So we have this. And then I'm going to regard this as a solution concept. All right, this is a good strategy. Does it make sense? So the strictly dominated strategies, I mean, coming from the idea of the strictly dominated strategies, we can sort of characterize the one solution concept. I said that there can be many solution concepts, but here is one solution. Okay? All right? So let's work on another game. I'm going to show you that strictly dominant strategy method does not always work. Does not always work means that it does not produce any meaningful result. If you look at that, in this case, you can actually see that neither player has dominated strategies. If you compare like these two guys for the player 2, it has to minimize that everything should be small, but not working. This is not working. This is, it should be maximized. It should be larger, but small. Larger. Okay, it's not working. CD, larger. Oh, actually this works, right? Minus 16. It has to maximize that. 5 is larger. 5 is larger than minus 16. 2 is larger than 0, and 3 is minus 1. Oh, I can remove that, right? Did I make some mistake? Probably. Okay, let's think about that. Okay, let's solve that. This is dominated, right? In player 1's perspective. But AC is not working, so let's compare these two guys. Should be small. Oh, this is small and small. We can remove that, right? And then larger. This is still not working. Should be small. Oh, this is small. Let me see. Yeah, so we can remove that, right? And then I can choose this. Oh, it's working. Yeah, I wanted to show the example. Did I make some mistake? Please correct me if you have. All right. I mean, what the original intention that I'm going to show you is that there is no strictly dominated strategy, so we need to be stuck and then working. I mean, we can come up with an example where we cannot remove any strictly dominant strategy, or probably I can just remove some of them, but we are left with a lot of numbers of the strategy vectors. I mean, please work on that. Maybe I make some mistake, or probably I chose some wrong examples. Interesting. Okay, probably we can change the number. So if that does not working, then we can change the number like 6. Yeah. If it's not working, then A cannot remove, and the B cannot remove, right? Yeah. I mean, the key point is that in many cases, the strictly dominant strategy, the removal method, does not work. Does not work means that we don't have any choice to remove. Okay? Okay? Right? So let's make the situation where we yeah, maybe I'm wrong. Okay, here. So the key point is that neither player has dominated strategy. So well, this method, well, in some cases it's working, but in some cases it's not working. So probably we require another solution concept. I'm not saying that which is better. Well, the equilibrium or the solution concept is is different from the people's perspective. I mean, the good solution concept should be able to find the equilibrium, well, as many as possible cases. Okay, but strictly dominated strategy removal method are too strong in some sense, meaning that for some games or for some large number of games that we cannot solve the problem. And there are some cases where we can solve the problem, but some other cases we cannot solve the problem, which means that the strictly dominant strategy removal method is not a good solution concept. I mean, in some sense. Okay. Right. So let's move on to the another solution concept. So another solution concept is something called the saddle point. Okay. So we'll look at that. So how should we analyze the game? Well, we're gonna run this algorithm. Well, why we run this algorithm? We're gonna look at that. So what we are going to do is that we look at just the first line, and then sort of draw the direction that we are going to do. In player 2's point of view, suppose that the player 1 is choosing A. Then out of A, B, and C, if this is chosen, I mean, assuming that this is chosen, obviously player 2 tries to minimize the number, so it has to this direction. I mean, I have a preference for the this -1. It means, okay. Now like that. In a similar way, if the player 2, okay, player 2 is suppose that the player B is chosen, then the player 1 will compare whether A is better, C is better, D is better. But it obviously it is easy to see that because player 1 tries to maximize the number, then this direction. And in a similar way, assuming that the player 1 is playing C, then the player 2 will compare the number, then we will have this direction. Right? So we will see that if we draw these arrows, then everything will be going here, inside here. Okay, I mean, what's the point of running this, drawing these arrows and so on? Well, mathematically, we are computing the saddle point of this game. What is a saddle point? Saddle point is something like this. Okay, because well, player 2's perspective, he tries to minimize that. Player 1's perspective, he tries to maximize that. Okay, so it's like from this perspective it's a minimum, but that perspective it's a maximum. There's a player 2's mind, and there is a player 1's goal, and then luckily we have a point which is meet with each other. All right. And then actually here in this case the saddle point is essentially if it is both less than or equal to any value in its row and greater than or equal to any value in its column, because the player 2 tries to minimize that and player 1 tries to maximize that, it is called a saddle point. And the saddle point principle is that the player should choose outcomes that are saddle points of the game. I mean, that's my belief. That's what I think about the good solution concept. Do you remember the dominance principle? Well, dominance principle is another principle, and I believe the saddle point principle makes sense. And there are some other people who believes that the dominance principle is a good choice. I'm sort of coming up with many principles, right? All right. So the right. So just as an aside, we often define the value of the game, where the value of the game is the value of the saddle point outcome if it exists. Now, probably you may ask the question: saddle point always exist? Right? That's the question, right? You might ask the question. That's a good question. Okay. Okay. Now we will see that saddle point always exists for the two-person zero-sum game. All right. But you might ask the question, why we should play a saddle point? Why saddle point should be a good solution concept? I mean, we have a little bit of a clue about what that is, because the player 1 tries to maximize the payoff and the player 2 tries to minimize the payoff. But let's dive into people's mind, or the player's mind, about why the saddle point is should be played by the people. Okay, so we're gonna look at that later, but I wanna talk about. Sorry, I wanna talk about. Let's see. Okay. All right. All right. So I'm going to talk about the saddle point existence later. Okay. So we first talk about the why should we play the saddle point. I mean, why is it is a good choice of the playing the saddle point. Okay. I'm going to talk about that part in the next lecture.